Linked list is a very popular data structure that has many applications, such as in building graphs, hash tables, LRU cache, and much more. But many people get confused when it comes to working with the internals of the linked list. Hi, my name is Prateek, and in this tutorial, I'll help you master the fundamental concepts of the linked list. But before we get started, make sure you check out free masterclasses on Scalar's event page from some of the best industry leading experts. The link is in the description below. Also, subscribe the channel if you haven't done already. Let's dive right in. Let us begin with linked list. What is a linked list? A linked list is a linear data structure in which the elements are represented as objects and they are stored in non-continuous memory locations. Okay. So one thing that you need to note about linked list is it's a dynamic data structure, right? So unlike an array where you need to tell, okay, I want an array of size n, you don't need to specify the size of the linked list. Every time you get a data, you create an object, you put the data inside it, and you put it in the form of a chain or in the form of a linked list, right? So why the name linked list? Because we have a lot of nodes. Okay, each node is an object in a heap, and these nodes are connected with each other, right? How they are connected? So each node is created at some memory. Let's say this address is 205. So the previous node knows that the next node is present at this address, right? So 2 will know the next node is present at some address. So that is also going to store there, right? So each node is going to store two things. One is your data and one is the address of next node, right? So if you know the address of next node, you can easily traverse the data structure and you can also put things in a ordered way, right? So every time you get a new data, we can insert at the beginning, we can insert at the end, we can also insert in the middle, right? So it's up to you how you want to maintain the ordering inside the linked list, right? One thing to note is it's a dynamic data structure, and the nodes in which the data is getting stored, they are stored in non-contiguous memory locations, unlike an array, right? So that is what linked list looks like, right? Now in linked list, we do not specify the size, as I have already discussed with you, and it is a dynamic data structure. It automatically changes size when an element is added or removed. So we'll go into the internals of how addition and deletions are performed on a linked list in this tutorial. So while doing the implementation, I will show you that, okay, if there is a node, how do I connect the next node? How do I add something in the beginning? How do I add something in the middle? How do I delete something, right? So the fundamental operations that we will be learning would be addition, okay, removal, right, and getting a node, right? So I want to get a particular node. How do I get that node, right? So given an index, I can iterate to that index, right? One thing that is bad about linked list is if you suppose want to get the middle node, right? In array, you can say, okay, give me the ith element. So this property is called as random access. So linked list is a bad data structure if you need to access ith element. Why? Because you cannot directly get this element. You have to traverse till I positions to get this element, right? So it's bad at getting nodes. It's bad at random access, but it is good at certain things that we will see. All right. So that being said, let us jump into the implementation of linked list. So now let us dive into the implementation of linked list. So far what we have learned is that linked list is a chain of nodes in which every node is connected to the next node, okay? If there is a node 1, it must be connected to the second node, let's say node 2, right? So the way to do it is that in every node, we also store the reference of the next node, okay? So for example, if this node is created at some memory location, let's say 206, then this node must store what is the reference of this node, where it is created, right? And for the first node, what we need to do, for example, if this node is created at some location 115, then we need to store this location 115 in a special variable, okay? We generally call this special variable as head, right? Okay. And second node will store the reference to the third node and so on, right? So third node, maybe it might be at 480. So I might be storing 480 here, right? Now the first step in the implementation is that how do we implement this structure, okay, this object that we see here. So we are calling this object as a node object, right? So what I will do, I will say, okay, I will define a node class, and this is capable of holding two things. One is my data and one is my reference, right? So each of these boxes is a node, right? So each node is going to hold a data. Now a data can be of a different type as well. So just for the sake of simplicity, I'm treating it to be a integer, but it can be an image, it could be a book, it could be any object, right? And second thing I have is a reference to the next node, right? So how do we store a reference to the next node, right? So I say, okay, this will be of the type node, and let's call this variable as next, right? So we have data and we have next. So if you're confused, I will explain you what is this concept. So let us first start with the code. Let us create this structure and let us try to understand that, okay, inside the node class, you can have an object reference which is holding the address of the next node, right? So let us go into IntelliJ, and I have created a package called linkedlist data structure, and here I'm going to create a Java class called as let's say node.java, right? Now it automatically creates a class for me, but it does not have data members. So how do I add data members? I can say, okay, I want data, and I also want something called as next. So that will be of the type node, right? Now this does not mean that there will be an object inside an object. No, this is only a way, this node, right? It's only a way to hold the address of the next node, right? So this is of the type object reference. I will tell you, right? And let me do one more thing. Let me add a constructor here as well. So you will see why we need a constructor. Let's do one thing. Let's create main, right? Let's create a linked list demo, another class in which I'm going to test my functionality. In this class, I will create my main method where I'm going to test my functionality, right? So let us create a node object. Guys, okay, node A, this is equal to new node. Right now, this does not hold any data, right? So A is not going to contain any data. By default, the value of integer is 0, right? And next would be null, right? So what I can do, I can say, okay, a dot data equals to 5, a dot next equals to null. And if I say, okay, s out a dot data, what I'm going to get, let us see, right? So I'm getting this value as 5, which is absolutely correct, right? Now why this is happening, let's see, right? So what it did, writing this code, it created a node, right? And what is a is referring to this node. So a is a address, right? A is a object reference. So a is another bucket which is holding the address of this node. So this node has two things. One is my data and one is my null. So this is your data and this is your next. And this node has been created at some memory location in the heap, right? This is my heap memory, right? So this address might be, let's say, 508, right? What is a holding? A is holding 508. This is what is exactly happening behind the scenes. So in this case, this a is also an object reference, right? And it is referring to an object. Inside that object, I have one more reference. Okay, how do I access this value? I access this value by a dot next. So this is what is happening when you are creating this node, right? So it is giving you, it's wrapping up two data members inside one bucket. Inside node, you have an integer value and a reference to the next node, right? If I say, okay, there is one more node, right? Let's say node b equals to new node, right? And I say, okay, a dot next should refer to b. So if I print out what is a dot next, so a dot next is nothing but it is the address of the b node that we have created, or the value that is getting stored inside b, right? Now if you see, this is the reference of the next node, right? So let me show you through a memory diagram. So a is referring to a node, okay? So a is 5, b is some other node. So let me do it like this. So a is a variable that is holding this address, let's say 108, this value is 5, and b is 30c, right? So b is some other node, b is another variable that is holding this value 30c, right? And this is the address of next node. I don't have any data and null value here, so it will be the default value of integer and next, right? So that will be 0 and null, right? So I have 0 and I have null, right? Now b is referring to this. So when I say a dot next equal to b, so inside a dot next, which is this field, I'm copying whatever is present in b. So I'm copying 30c. So it means, in a way, this b got connected with a, right? Now even if I lose this variable b, this chain is still connected, right? So this is how we are going to work with nodes, and we will write one more class that does all this manipulation of nodes. Okay, so we'll call that as a linked list class, right? So I hope this node concept is clear. What is a, what is new node? The new node is getting created in heap. In this case, this is a reference variable here, and this variable is created inside stack at this point, right? So what I will do, I'll remove all this code, and I will do one more thing. So instead of like every time doing a dot data equal to something, a dot next equal to something, I will define a constructor inside this class. So I call it as node. It will accept some integer, let's say data. It will accept some value of next, but in general we will not know that value of next. Okay, so whenever you creating a new node, you know the data. You say, okay, I want to create a new node with data 7. Now what will be connected in the next node, we do not know at the moment, right? So what we can do, we can leave this variable initialized with the default value, right? So I can say this dot data equals to data. So I'm initializing this variable with the data that I'm getting, right? So since the two variable names are same, writing this here is important so that compiler knows that we are talking about this data member as an attribute, right? And next, what about next? So you can say next is null, or you can say this dot next is null. Both are fine, both will work, right? So this is the constructor for the node class, right? Now if you want to create a node a, now you will say, okay, node a equals to new node. You just give the data as 5, and you say node b equal to new node. You say data is 6, and a dot next equal to b. So this creates a very simple linked list in which we have two nodes. Okay, so if I say s out a dot data and show me what is the data in the next of a, so how do I do it? A dot next gives me the address of b dot data. So I'll say 5 followed by 6, right? So I will see this. So I see 5 followed by 6. So what we did, we simply created a linked list in which we have just two nodes. This is a, this is b, right? Okay, and a dot next is storing b. So a dot next is storing, right? Now you might say, okay, this looks very easy, but if I have to add 10 nodes, 20 nodes, 100 nodes, 1000 nodes, will we create so many variables and attach them manually? The answer is of course no. We will write an algorithm that does insertion in the linked list, deletion in the linked list, and it helps me to get the nodes in the middle of the linked list, or at the end of the linked list, or at the beginning of the linked list, right? So to do all these operations, what we will be doing, we will be writing our own linked list class. So what I will do, I'll create a new Java class, and I will call it as linked list.java, in which all these operations involving these nodes will be done, right? So let's see the implementation of linked list. So let us see the implementation of linked list. Now suppose you are you want a data structure that is like in the form of a chain, right? And you want to build certain methods. You want to say, okay, I want to do addition in this linked list. That means I should be able to add more nodes inside it. I should be able to remove nodes from this linked list, and I should be able to get the nodes from this linked list. That means I want to read nodes from the linked list, right? Now the add operation, it can happen at 3 places, right? So maybe if there is a linked list like this, you can say, okay, I want to add something in the beginning of the linked list. So I can say, okay, add at the first position. Or you might say, okay, I want to add something after the last node, right? So you might say, okay, I want to add at the last node. Or I might want to say that I want to insert something in the middle. So I might be doing something in the middle or at a given location, okay, at a given position inside this linked list, right? Similarly, remove can happen at the beginning. So I will say remove first would be an operation, remove last would be an operation, and remove at a particular position can be an operation. Similarly, get means, okay, I want to read something, I want to get the first element, I want to get the last element, or I want to get the middle element, right? So I will say I want to get first element, last element, and element at a given position, right? So what we will be doing, we will be implementing these operations, right? Now in order to implement these operations, right, what is important? Let us start by understanding how my add operation will work, right? So whenever you want to add something, so one thing you need to know is what is the starting point of the linked list, right? So suppose you want to add something in the beginning, you must know the starting point, or you want to add something at the end, right? Now, one way is if you're adding something at the end, right? That means if you're creating a node here, you must access this node and update the next variable of this node, right? You would say, okay, in the ending of this node, I will attach this node. So one way is you always iterate till this point, starting from the head, and this will actually take order of n time. If you iterate from here to here, it will take order of n time. So I don't want to do that. What I will do, I will say, okay, every linked list will at least know what is my head and what is my tail. So I will keep another reference that always point to the last node of the linked list. Whenever you will add a new node at the ending of the linked list, I'll say, okay, I'll modify the tail node, I will attach the node, and I will update my tail variable to go here, right? So let us see how these operations are implemented. So what I'm trying to tell you is that if you're implementing a class called linked list, this linked list will have data members, okay, something that the linked list should know, okay, and some operations that the linked list will does, right? So here are the operations, they will be part of the methods, right? And we will have some data members or attributes. What are the data members? What are the things that the linked list must know? One is head, what is my starting address, one is the tail, what is my ending address. So again, keeping this is optional, but I want to optimize certain operations. For example, add at last should not be an order n operation, it should be an order one operation. So I need to keep the tail variable as well, right? And maybe some optional information like size, how many nodes I have in the linked list. Okay, so maybe I want to implement a method like get size, how many items are already inserted in this linked list. So this is a useful operation. We want to check, okay, if the size is 0, that means linked list is empty, right? Otherwise, you can check if the head is null, that also means linked list is empty, right? So we will also implement this operation like get size, and maybe we'll implement operation like display. I want to show the entire linked list, okay? Or you can implement a method like toString, iterate on this linked list and convert it into a string. So that is just like a display method. I want to show the entire linked list to the user, right? So let us start by implementing these operations one by one. So this is my linked list class. So first of all, what I will do, I will add some data members and I will add a constructor to it. Else, okay, I want to create a head. So node head, right? Again, head is a object reference, hence it has a data type called as node, right? Then I will have node tail, and one thing I can do is I can make them private. So private node head and private node tail. I don't want people outside the linked list class to know where is the head node, where is the tail node. So I will not expose this data outside the linked list class, right? And I can also say private int size. I'm not making it public because I don't want this size to be changed by someone outside. The size should change automatically when something is inserted or something is removed from the linked list. So it should be a private variable only changed by the linked list class, right? Next thing I want to do is I need to initialize a constructor, okay? Whenever user says, okay, give me a new linked list, what should I do? So that linked list will have 0 nodes inside it. So I need to initialize these 3 data members as well. Else, okay, linked list, there is a constructor here. And what I want to do, I want to say head and tail, they will be null and the size would be 0. Okay, so this is my constructor. Now what is the first thing I will do? Else, okay, I want to do an insertion. So I'll write 3 methods, one to add something at the beginning, something at the end, and something at a given position in the linked list. That's okay. Public method, and the method is of the type void add, and let me call it as add first, and public void add last, and public void add at a particular position. So add. So in all the 3 methods, I should know what is the data that I need to add. And in the third method, I should also know at what index I need to add, right? Now take a pause and think, how you will implement these methods. Okay, if you're given a linked list and you want to add something at the beginning of the linked list, how you would add in. Okay, so what will be the code behind this method? Take a pause and think about it. Okay, so let us discuss the first method, add first. Now suppose you have a linked list, right? Let's say this is A, this is B, this is C. This is already there and head is referring to this node. I want to say, okay, I want to add another node D, which is at the beginning of the linked list, right? So how I will do it? So first thing is I need to create this node. So how do I create a node object? Very easy. I simply say, let me create a node called as N. This is equal to new node, and the data of this node is same as this data that I've given. So this creates a new node and N is referring to this node, right? N is an object reference, a local reference created inside this function, which is referring to this particular node. What should I do? How do I connect this? So I would say, okay, N dot next should refer to the head. So if head is already there, N dot next should connect to head. So it makes this connection, right? One thing I need to do is I need to say, okay, this head, it should move here, right? This head should not refer to A, instead this head should refer to now D. So I can say head is equal to N. So this will work really well. And one more thing I will do is size plus plus. Every insertion will increment the size of the linked list, right? So this will work really well if the linked list is already there, right? But suppose you're creating the linked list for the first time and you call the add first method. So head and tail both were null, right? And you said, okay, I want to create a new node. So you created a new node called D, and N dot next is equal to head. So head was null, so D's next is also null, which is fine, right? And then you say head is equal to N. This head refers to this node, which is also fine, right? But the thing is, the tail is not getting updated, right? Whenever the first node is inserted, right? Let's say the first node is A, both head and tail should refer to this node, right? So what I can do, I need to add a separate condition that if if the size was 0 before adding this node, in that case my tail will also get updated. So tail should also point to head, or tail should also refer to N, right? Now this is a special case when you have 0 nodes. In that case you also need to update the tail, right? So this is my add first method. Now let us test the functionality of add first method. So what I will do, I will go in linked list demo. It's okay, I want to create a linked list. L, this is equal to new linked list. And now in this, I can say, okay, L dot add first, and I will give some data, let's say 10, and say L dot add first, I will add 20, and then L dot add first, I will add 30, right? So I want to see this linked list. So I will call the display method, which I have not implemented. So we will implement the display method as well, right? Let us go back into the linked list class and let us add one more method, public void display, right? So how do I display the linked list? Now it's going to be pretty easy. Suppose the linked list is 30 followed by 20 followed by 10, right? And head is referring to this node. Okay, tail is referring to this node. This is 10, right? So tail is referring to this node. So what I need to do, I need to start iterating from head till the end. So I'll say, okay, I'll take a temp variable, I will print it, and I will take temp here. I'll print it, I will take temp here. I'll print it, I will take temp here, right? So what is happening? So once my temp reaches null, I will stop. What I can do, I can say node temp, this is equal to null. So temp is again a reference, it's not a node, right? So sorry, it's equal to head. It starts from head, and while this temp is not equal to null, what do? I print the node. So I say sout temp dot data and take this temp to the next node. Temp equals to temp dot temp goes to the next node. This while loop will help me to iterate on the entire linked list, right? So temp starts from head, temp is referring to this node, I print out 30, temp equal to temp dot next. So temp dot next means this value. So this value means this node. So temp goes here. Again, temp dot next means this value. which is this node. Temp goes here. Again, this is not null. This node is not null. So I say temp dot next, which is this value, which is null. So temp actually becomes null and my loop stops, right? Now the display method is there and we can run this code. Okay, so I see 30, 20 and 10, which is okay. That means my linked list is getting created. But to show you in a linear fashion, what I can do, I can put an arrow here and I can put a new line here, right? This will make the representation look little better, right? I'm getting 30, 20, 10. Now, if you look carefully, I added 10 in the beginning, so 10 got added. That means my head and tail both were here, right? Then I added 20, in which 20 got added here and my head moved here, right? Then 30 got added, a new node was created, it got connected here, and then my head moved here, right? This is how the linked list is going to look like: 30, 20 and 10. So I hope you're able to understand the add first method, right? Now on the similar lines, what we will do, we will implement the method called as add last. Now take a pause and think how you will implement the add last method. All right, let us see, right? Now suppose you already have a linked list A, B, C, right? And I want to add a new node D, which is at the end of the list. So this is my head and this is my tail, right? So how do I add a new node here? So first of all, I need to create this new node. So how do I do it? I can say, okay, fine, node n, this is equal to new node, and I give the data to this node that I'm getting, right? Now how do I connect this tail node with the new node? So that connection is pretty easy. What I need to do, I need to update this value and give it the reference of this node, which is stored in n, right? So I need to say that fine, tail dot next, this is equal to the new node that we have created, right? So this makes the connection, and I also need to say, okay, this tail should be here because this node is now the new tail, right? So I can say tail equal to tail dot next, or you can say tail equal to n. Both are fine, right? Now this tail has also moved. And one more thing we will do is we will just size plus plus. Now this will work fine when the linked list is already there, right? But think of a case when your linked list is not created. That means both head and tail, they were null, and you inserted the first node by calling the add last function. You say, okay, I don't have a linked list. That means if the size is 0 and you're adding the first node in the linked list, then how should the update should happen, right? So you still created this new node n, right? With the data d, n is referring to this node. So in this case, both head and tail should get updated. They should point to this node, right? So what I can do, I can say, okay, head and tail, they will refer to n, right? They will also store the address that is stored in n, right? Now you might ask, okay, what happens to this n? So n is a local variable. It will get destroyed after this function call is over. But head and tail, they are the data members of the class. They will exist till you have the linked list object in your memory, right? So they are not going to get destroyed, right? So n is a local variable. It will be over, right? And anything that is allocated using new will not get destroyed. Why? Because if someone is referring to this memory, that memory will not be garbage collected, right? So head and tail, they are referring to this node. N is a local variable. It will get destroyed, right? So this way add last will work. So now let us test our functionality, right? So I say, okay, l dot add last, maybe this is 40 this time, and again I say, okay, l dot add last, this is 50, right? Now if you look carefully, I'm adding the first node by calling add last function. First 40 was added, add first 10, so 10 was added, then 20 was added, then 30 was added. Now again I'm calling the add first method on a linked list which is already built. So 50 should get added, right? So if I say l dot display, right, it will give me this linked list. Let us see the output. So we are getting this linked list 30, 20, 10, 40, 50. That means this is working really fine, right? Okay, let us go back here and let us implement one more method. That is, okay, give me the size, right? How many nodes we have. So that's going to be easy. Public int get size, and what we are going to do, we are going to return the size of the linked list, right? Now we are doing it this way because if you make this size public, anyone can change it, right? So I'm only giving the getter to access the size. I'm not giving any method to set the size of the linked list. Okay, so that size should be updated only through the add and the remove methods. So this is also fine. So I can say l dot get size, and I want to display how many nodes I have in this linked list. This is again a order one operation, right? So I can say, okay, there are 5 nodes. Now let us talk a little bit about the complexity. So your constructor is doing order one work. At first, it is also doing order one work. No loops involved. Here also we are doing order one work. Get size, we are doing order one work. Display, we are iterating over all the n nodes. We are doing order of n work, right? Now the next method is add, right? So take a pause and think how you will implement add method, and if you want to insert something in the middle of a linked list at a particular index. Okay, so let us see it next. So we are discussing how do we implement the add method. Okay, so we are given, okay, this is the data that you need to add, and you have a particular index at which you want to do this insertion, right? Now suppose my data is 4 and my index is 3. That means, okay, 0th index, first index, second index, here I want to add, like at the third index the new node should come, right? Or you can say, okay, after 3 nodes I want to insert the 4th node. So this is my 4th node that I want to insert somewhere here, right? So how I will do it, right? So one way is, okay, I will create a new node, n is referring to this node 4, right? But how do I connect 3 with 4 and 4 with 5, right? So this is going to be easy. How? You can say, okay, let me create this new node n. So node n, this is equal to new node with my data 4, right? Now one way is, okay, I can say I need to reach this node, right? How do I reach this node, right? That means if I start from this node, right, and I want to reach the third node, right? After 3 nodes I have to insert. That means I have to reach the third node. So if I take one jump here, I reach 2. If I take one more jump here, I will reach this node, right? That means in order to reach 3, I need to take 2 jumps, right? Okay, so if my index is some p, right, I need to take p minus 1 jumps, right? For a particular position p, I need to take p minus 1 jumps. This we will do it using a loop, right? Let's say I've reached this node and I'm holding this address in a variable called temp, right? Now how I will do it, right? So I can say, okay, temps next should point to 4. If I do this, temp dot next should refer to n. What loss I will have? I will lose the address of 5. I don't want to do that, right? How should I do it? I will say that before doing this operation, let me say that 4 should store the address of 5. Can I do that? Of course, yes. So how do I do that? I can say n dot next, that is the next of 4, should refer to 5. So what is the address of 5? It is nothing but it is the next of temp. So it is temp dot next, right? Once it is done, can I update the address, the next of 3? Of course, yes. I can say, okay, 3 is next, now should point to 4, and this link will automatically get broken. So I can say 3 is my temp dot next should be equal to n, right? So in just these 3 steps, I will be able to insert a node in the middle, right? Now we might have a special case where we might need to insert a node in the beginning or at the end, or we are getting an index which is out of bounds. So let us see how we will handle those cases. So first of all, I'm going to check if this index is out of bounds, right? So if my index is less than 0 or my index is greater than the size of the linked list, that means I cannot insert this node, right? So in this case, what we can do is either we simply return, right? But that's not a good idea. We should tell the user that you are doing something wrong, right? So one way to do it is we can throw a new exception and we can say, okay, index out of bounds, right? That you're using the incorrect index. And here I have to say, okay, this method throws a exception, right? So I can throw an exception in this case, and an error will come in the main when this program is executed, right? And now if my index is 0, that becomes a special case. That means, okay, I'm trying to add something at the beginning, so that I have already handled. We can just call the add first method with data, right? So I can say you call the add first and you give the data. That's it. Else if your index is equal to size, that means if the linked list has 3 nodes and you want to insert something at index 3, that means you're inserting something here, right, which is again at the ending of the linked list. In that case, you can call the method add last and you can give the data, right? So in the else block, we have to write the exact logic that we are talking about, right? So let's see how we will do it. Suppose your linked list is like this: 1 2 3, right? And I have 5 6 7, right? So I'm telling you that, okay, after 3 nodes you have to insert a data that is 4, right? So how do I do it? First I need to reach the third node, right? So I need to take a temp and reach this node. So temp will start from head. So I can say node temp, this is equal to head. How many jumps I have to take? I have to take index minus 1 jumps. So I can say, okay, for int jump equal to 1, jump less than equal to index, right? Jump plus plus, right? Or if it is sounding confusing to you, you can say less than equal to index minus 1, right? These many jumps, as I told you, we have to take, right? Now in each jump, what we should do, temp will take a step. So temp will go to the next node, temp equal to temp dot next. Now I'm in a good position to do some insertion here, right? What I will do, I'll say, okay, let me create a new node n whose data is 4. So I can say node n, this is equal to new node with the given data, and n dot next should refer to temp dot next, as we have just discussed here as well, right? So 4 should get connected with 5. That is the first step. Then I need to connect 3 with 4, right? So how do I do it? So 3 is my temp dot next should point to 4. So 4 is n. That's it. And size plus plus. Size we will update here. So here we are not doing size plus plus because add first and add last will automatically increment the size, right? That's it. So that is my insertion in the middle. Now let us run this code in main and see if it works really well or not, right? Now I can say, okay, this was my original linked list. L dot add at index. Let's say I want to add at some index 0. Let's say the data is 0, right? L dot add at index. I want to add something at the last index. So L dot get size. Okay, now I'm getting not add last, but I can say add at. So index will be, let's say, the last index. So data is, let's say, 100. L dot get size. Now again, here I'm getting this because I've not written throws exception. So main can also throw an exception because it is calling a method that throws exception. So main can also throw exception, right? So we have to write this here, right? And let's add something in the middle as well. So L dot display, and I will say, okay, L dot add at index 4, sorry, data is 4 at some index, let's say 3, right? Something like this. And again, let me say L dot display. So this will test our all the 3 cases, and we should be seeing that they should work fine, right? So in the first case, I added 0 in the beginning, fine. I added 100 at the end, fine, working fine. Then in this linked list, I said, okay, at index 3, I should insert 4. So 0, 30, 20. This is the third index. So before 10, I will insert a 4. So 0, 30, 20. I'm getting a 4 here. Then 10, 40, 50, and 100. That means in the middle, it is also working fine. And I display this list, right? And finally, I have 8 elements: 1, 2, 3, 4, 5, 6, 7, 8. That means that size update is also working fine in all the 3 cases, right? So that completes part one. That means we are able to add nodes in the linked list in all the three cases. We have seen add first, we have seen add last, and we have seen add in the middle, right? Next, we will move on to get, and after that, we will move on to remove. Right? So take a pause and think how you can implement these methods: get first, get last, and get an element at a particular position. It's your time to code, and I'll just show you the add at method, right? So pause this video here and try to implement these three methods. Let us implement the get method, right? So I need to write a method called public int get first. That means I want to get the first element of the linked list. But what if the size of the linked list is 0? I do not have any such element. So I will have a special case. If size is 0, I can throw a new exception that the linked list is empty, right? So linked list is empty. That is the error that I'm trying to show to the user, right? And here I have to tell that, okay, this method also can also throw exception, right? So throws exception. But if the size is not 0, the linked list is there, then it is pretty easy. We just need to return the data present in the head node, right? So head is referring to this node, access the data and return it. So return head dot data. That's it. Size will not change, and this is what you will do. So similar to this, you can also write get last. So again, if the linked list is having size 0, then there is no last element. You will throw an exception, and in that case the last data will be at the tail node, right? You can say return tail dot data. That's it. Now if you want to get something in the middle, that is going to take one more step, because you will have to loop through it, right? Okay, so add at we did not discuss. It's going to take order and time, because your the worst case you might have to loop till the second last or the last node, right? So get last we have done. Now this will be get at a particular index. If I give you an index and I want to get an element at that index, how it will work out? So take a pause and think how you will do it. So this is also easy, right? Now user is giving you an index. Now it is possible that this index is also out of bounds, like we saw here, right? Like in the case of addition, it is also possible that this index is out of bounds. So if index is less than 0 or it is greater than size, I can throw an exception index out of bounds. Then if this is not the case, right? So if this is not the case, if the user is uh, really giving you a valid index, right? Else if it is possible you're talking about index 0. If that is the case, you can say return get first. This can happen. Else if index is equal to size, you can say return size or size minus 1. It will be size minus 1, because the last element will have an index size minus 1. You can say return get last, right? Otherwise, what you need to do, you need to iterate on the linked list, right? So that iteration part is easy. What we will do, we'll have, let's say, A, B, C, D, and so on, right? So this is index 0, 1, 2, 3, 4, right? So I want to get something at the second index. What I need to do, I need to take one jump, one more jump, two jumps to reach this particular index, right? So that means take the number of jumps equal to that index. So I can say, okay, fine, node temp that is equal to head, and for int jump equal to 1, jump less than equal to index, jump plus plus. What do? I take my temp to the next node, temp equal to temp dot next. Once I reach this node, I need to return the data of that node. So return temp dot data. That's it. So I take my temp here and I return this data, right? This will give me the data at a given position. So that is my get at a particular index. Now let us test this code. So I want to say, okay, fine. In this linked list that we have, I want to get the 0th element, s out l dot get first, s out l dot get last, and s out l dot get at index 4. Let's go and run this code. The first element is 0, last element is 100, the fourth element is 10. Let us verify. So 0th index, first index, second index, third index, fourth index. So fourth index is really 10. That means my output is correct. That is how we build the get at methods in the linked list. So far we have seen the add method and the get methods. Okay, all the three versions. So getting first, adding first, they all take order one time, but doing some work at a particular position, they take order of n time, right? So other methods are all one. Now we have the remove method. We want to remove first, remove last, and remove at a particular position. So let us see how we will write these methods. Okay, so what I will do, I'll create remove methods, public int. So remove, I will also get the data that has been removed from that particular index. So return type would be int. So remove first. You might think it should be very simple. Whatever is at the head, I will return that, right? So I want to remove this. Let's say 10 is there, 20 and 30, and this is my head. How do I remove this node? So one way is, okay, you can store the output, that is going to be head dot data, and then you can say, okay, this head will move to the next node. So head will go here, right? So head is going to be at head dot next, right? So doing this, will it remove this node? The answer is yes. So in heap, this node is a node that no one is referring to. What will happen? It becomes eligible for garbage collection. So garbage collector will come and it's going to sweep away this memory. So that means now your linked list will be only this, right? But there are few special cases, right? So I can say the output will be returned. That's okay. You also need to reduce the size. This dot size minus minus. This is something we need to do, right? But what is a special case? If the linked list is empty, can you remove the first element? The answer is no. So we have to check if the size is 0. What we will do, we'll throw an exception, right? We'll say throw new exception that linked list is empty, right? Fine. And we need to tell that this method throws exception. Now what about if the size is 1, right? So head will get updated, fine. But if you have just one node and both head and tail, they were pointing to this node, will it form a special case? Of course, yes, right? So if this node is getting removed, what will happen to head and tail? They will be reset to null, right? If your original size was 1, how do you remove it? You will set your head and tail equal to null. Size will become 0, right? Okay. And else, sorry, yeah. So one thing we can do is this code we can move here. Output is equal to head dot data. Okay, and we'll of course return output. This code we can move in else case, right? That means if there are like at least two nodes, in that case tail will not be affected, right? So what about this case, else case? If there is 10, there is 20, and there is 30. So this is my head, this is my tail. Even if my remove this node, head comes here, right? So head goes to the next place, size gets reduced, so tail is not affected, right? But if I have just one node and I remove that node, in that case head and tail both will be affected, so they are reset to null and the size becomes 0. So that is how the remove first method should work. Now let us test this method. Let me create a new linked list. Let's say I add at the first position, let's say 10, then I add 20, 30, 40, 20, 30, 40, and I can say L dot display. Then I can say L dot remove first and L dot display, right? So I'm getting 40, 30, 20, 10, fine. And if I remove the first element 40, my linked list is 30, 20, 10, which is fine. Okay, if I have just one element in the linked list, and let me see if it works well. So I have one element, I removed that one element, so my linked list is empty, fine. That also works well, right? And I can say s out L dot size, I want to see if my size is getting updated properly. Yes, the size is 0 and I don't see any output here. That is how I will implement remove first method. Now on the similar lines, can you implement the remove last method? Okay, just need to think what will change, what will happen to head and tail, how much time it will take. So this method, it's going to take order one time, right? Remove first, but you have to think how much time remove last will take. Okay, so let's see remove last. Okay, so first case is, okay, if your linked list is empty, you cannot throw anything, you cannot remove anything. So if your size is 0, you will throw a new exception. Okay, then similar to this one, your output in this case will be what? Your output will be now tail dot data. You know, the last node is tail and that data is your output, right? So if your size is 1, what you will do? You will reset your head and tail to null and you will say size is 0. If this is only one node, both head and tail are referring to this node, you want to get this data, you store this data in a variable called output, that is tail dot data. Original size was 1. So if this is removed, head and tail, they are reset to null and size becomes 0, which is correct, right? Otherwise, if you really want to remove something, right, so you will have to check that if your index is in the bounds, or is it 0, or is it the last index. Sorry, you don't need to check here because we are talking about remove last, right? So you just need to remove the last node, right? So what I will do, I'll say, okay, else we have the other case, we know what node to remove if there are more nodes, right? There is one tricky thing here, that if it is a single linked list, right, and this is your tail node, you're saying I want to remove this node, right? That means tail should be updated, tail should come here, the new tail should come here, right, after removing this node. So I've stored this d in a variable called output. So output is tail dot data, so output is d, right? But how do I bring it back? There is no way to do it, right? Even if you maintain, okay, I'll maintain previous of tail for every node. Suppose this was the previous, but when you remove C, how you will get the previous? So the answer is, we don't have any order one way of coming to the previous node. We have to iterate from the beginning to reach this node, right? So that I can update my tail variable, right? So this is going to take time, right? Or the other option is you maintain a doubly linked list in which every node is also connected back, right? If you do that, your remove last will work in order one time. But for now, we have a singly linked list. That means we have only the next address, right? Singly linked list. In that case, we have only one option: start from the head node and try to reach the second last node. So how do I do it? So I take a variable called temp, which starts from head. I can say while temp dot next is not equal to tail, right? So what is the stopping condition? So when I reach this node temp dot next, this is equal to tail, right? So this is the tail node, right? Suppose this is my C, this is my temp, and this is my tail node, this is my D, right? So I'm saying while temp dot next is not equal to tail, right? Until this condition is not met, I will take my temp to the next and next node. So temp starts from here, it goes here, it stops here, right? Because C's next is equal to tail, so temp will stop at C. So I can say temp equals to temp dot next. My temp stops at the second last node, right? Now why this is important? Because I want to update the tail thing, right? Now at this point, I want to disconnect D. So this D I don't want. So what should I do? I would say temp dot next is equal to null. So if I reset this variable to null, what will happen? This object becomes eligible for garbage collection because no one is referring to this object, right? So garbage collector will come and sweep away the memory of D because there are no object references which are holding the address of this node. So this D will get deleted from the memory and C's next is updated correctly, right? But what about the data that we wanted to return? That is still copied in a variable called as output, right? So once this is done, what should I do? So temps next is now null. This tail should be updated. So this tail should come here. So this tail will become equal to temp and the size will also get reduced, right? So here we have reset the size. So here it will be one lesser, size minus minus. That's it. And I will return the output in both the scenarios, right? So return output. In this case also I'll return the output. In this case I will also return the output. That is how remove last will work. And if I now show you l dot remove last, and maybe if you want to output, that's okay. We just want to see the linked list. So I can say l dot display. What do I get? Okay, let me add some numbers, only then we can see. 20, 30, 40. So right now I'm getting an exception because it's an empty linked list. So 10, 20, 30, 40 l dot display, and then I called the remove last method. So this was the linked list. I removed the last element. This is what I am getting, and the size is 3, right? Which is fine. That means the remove last is working as expected, right? Now the next thing we would like to do is, any guesses? Of course, it's going to be remove at a particular index. So we want to write one more method, public int remove at a given index. So again, before I write the code, take a pause and think how you will implement this method. Given a particular index, I want to remove something from that index. So let us start implementing a remove at, right? So first thing is, if the size is 0, that means you cannot remove anything. So you will throw a new exception. So throw exception, throw new exception, and you will say, okay, linked list is empty. You cannot remove it. Or you can check that if the index that you're getting is out of bounds. So if index is less than 0, or your index is greater than size, you cannot remove, or equal to size. Even at size we don't have anything. The last index is size minus 1. So if this is the case, I have to throw new exception, right? I'll throw a new exception, and we'll tell that this method can throw an exception. All right, so the error is fixed. Now what to do? I still want to remove it. So if my index is 0, that means I want to remove something from the head that we have already implemented. So whatever is returned by the remove first, we will return that. Else if index is equal to the last, which is size minus 1, we will return whatever is removed by remove last method. And now is the time we will see the actual working of this method, right? How do I remove something from the middle of the linked list? So let's say I have a linked list like this: A, B, C, D, E, F, right? And I say, okay, I want to remove something from index 2, right? 0, 1, 2. I want to remove this element. So if I want to remove this element, that means B should get connected with D, right? And this link from B to C, it should get broken, and C should be garbage collected, right? If this happens, C will be deleted from the memory, right? So how we are going to achieve this, right? So first of all, we need to reach this node, that is B, right? So if my index is 2, I need to reach one node behind that index. So how do we reach that node? Again, fairly easy. I can say I will start with temp, that is equal to head. And if index is 2, that means I need to iterate one less than that index. For int jump equal to 1, jump less than index, jump plus plus. So if it is 2, I'll just take less than 2 jumps. That is, I'll take one jump. I will come here, and at this node, I will start doing certain operations, right? So first of all, let me take temp to that particular node. Right? Now I'm standing at this node. So what I want to do, I want to return this node, right? I want to return the data of this node. I will copy it in a variable called output. Output is nothing but temp dot next dot data. That is what my output is, right? And I want to return that output. Or let's say this is my node, which is okay. Either way we can do it, right? Node called output. So this node is my output node. And what I want temp to connect with next of this node. So I want B to connect with T. So how we can do it? So temp.next, either you write it should be equal to temp.next, which is my output dot next. So that is my D. Or you can say output.next. So again, I'm connecting B with D, right? Now no one is pointing to C. It will get garbage collected, right? Okay. And if this node is garbage collected, this link is automatically broken. So what I need to do, I need to say size minus minus, and I need to return output dot data. Output dot data. This output is a local variable, right? It is there only in this function. Once I return output dot data, there is this function call is over. Output will be out of scope. It will get destroyed, and hence no one is referring to C. This memory will also be cleared off. That's it. That's what you need to do, right? So that is going to remove something from the middle of the linked list, right? Now I can test my code. So I can say l dot remove at index, let's say 1. So given this linked list, let's say remove at index 2, which is okay. Show me what will happen if you remove something from index 2. So this is my linked list. And if I say, okay, remove index 2, 0, 1, 2, 20 is gone, I get 40, 30, and 10. That means the code is working absolutely fine. So this is how we can remove something from the middle of linked list. So far we have seen the implementation of single linked list, right? So in which we said every node is going to store the address of the next node, right? But what happens in real scenarios, you might need sometimes a doubly linked list. So what is a doubly linked list? So just like you were storing the next, you will also store the address of the previous node. That means each node is now holding three things: data, a next reference, and a previous reference. So 2 will hold the address of 3, 2 will also hold the address of 1, right? Now the advantage of doubly linked list is that you can traverse in both directions, right? For example, we were doing removal at tail, in which I said, okay, I want to remove this node and I want this tail to come back. So if it is a single linked list, I have to iterate from the front to reach this node, which is going to take order of n time, right? But if I do it the same operation, deletion at end, for a doubly linked list, I can just come back to the previous node, okay? Because 4 knows the address of 3. So I can update my tail pointer very easily, right? So it comes at the cost of extra memory, but it can save some time. For example, if you want to delete something at the end, it can then be done in order one time. Insert at end can be done in order one time. Insert at head can be done in order one time. Remove at head can also be done in order one time. Right? So at both ends, you can do insertion and deletion in order one time, right? So each object stores data and memory location of next as well as the previous object, right? So this is something you can implement, right? Now there won't be a lot of change. For example, if you're making a method to insert something in the middle, let's say I want to insert 5 here. What are the variables that you will have to update, right? So you will have to update that 2's next should point to 5. Okay, but if you do this first, what will happen? You will lose the address of 3. So what I will do is, I'll say, okay, let me create this new node 5, and let's say this is my temp. Here I want to insert it. So 5's next will point to 2's next. So 5 gets connected with 3, right? I can also say 5's previous can point to temp. So 5 also connected with 2, right? Now I just need to change these variables. So I can say t's next will point to n. So 2 points to 3, right? And I also need to say 3's previous, right? Or we can do it other way, right? We can first say that this node, which is the next of 2, so t dot next, right, dot previous, 3's previous should point to n. So this link will get like this. This link is gone. Now what you can do, you can remove 2's next and make it point to n. So you can say this will get connected here. So you can say t dot next, this is equal to n, right? So again, you just need to think logically, and you need to execute these instructions in a particular order so that your updates are correct. You're not making any changes which are inconsistent, right? So again, all the operations get remove, add. You can try creating those operations on a doubly linked list as an exercise, right? So let's talk about what happens in Java, right? So if you want to use this class inside your collections framework, then this class is already implemented. So there is a class called as linklists. So it's part of java.util package as a part of collections framework. By default, this class internally uses a doubly linked list, right? So if you're using this class directly in solving problems, you're getting a doubly linked list by default, right? So if you want to learn more about this, I have covered collections in my DSA tutorial on the channel. You can watch that and learn how do we use the inbuilt doubly linked list or inbuilt linked list class. You can definitely learn about the methods of that as well, right? So let us quickly revisit the features of linked list, right? So it provides us an ability to use the non-continuous memory locations, right? So if you have like different chunks of memory available in different parts of the heap, and you cannot create a big array, but what you can do is you can use some memory here, some memory here, some memory here, and you can just connect those chunks, right? Non-continuous memory parts can be utilized efficiently using a linked list. Second advantage is it's a dynamic data structure. There is no need to allocate pre-memory, and again this results in efficient utilization of memory. For example, if an array you say, okay, I need 1,000 elements, but only suppose 100 get used up, then what is happening? All this memory is it's a waste of memory. It's not efficient utilization of memory. So linked list, you create memory on demand, and hence you only use that much memory that is required, right? Okay. And if you are using a doubly linked list, insertion and deletion at the ends of the linked list, they are performed in constant time. So if you compare it with an array, and if you have to do some insertion or deletion in the beginning, right, you will know that it's going to take order of n time, because I have to do shifting. If I insert something or if I delete something, again I have to shift all the elements, right? And joining two linked lists is much more efficient in terms of space and time. So if there is one linked list and there is another linked list, right? So think, if you have to join two arrays, you have to copy all the elements from one array into another array. But if you have to join two linked lists, you just need to connect the tail of one with the head of other linked list, and that is going to be again an order one operation. So it saves both your space and time, right? So that is all about linked list. So a quick revision on the operations. Random access, if it is a linked list, it's a bad thing, right? Because it's going to take order of n time. In an array, getting the ith element will take order one time. Insertion and deletion at the beginning, order one time. In an array, it's going to take order n time, as I just discussed. Insertion and deletion at the end, right? So this, if it is a doubly linked list, it can be done in order one time, right? In an array also it can be done in order one time. Insertion and deletion from a random location, so if you're doing somewhere in the middle, both are going to take order n time, right? So in an array, this part is bad. Insertion and deletion at the beginning. Random access is good. In a linked list, this insertion deletion part is good, but random access is bad. So you can see each data structure has its own pros and cons. So depending upon the problem, you have to decide whether you will go with a linked list or an array. So that's all for the video. If you found the video helpful, hit the like button, share it with your friends, and don't forget to press the subscribe button. I'll see you next time.